Hello everybody and welcome to our video on areas in the definite integral, part 2. So in the last video we had talked about how we were using areas under curves to evaluate integrals, and then we extended that to approximating the net area under a curve by using rectangles to approximate the areas of each subinterval. So now to rigorously define the integral, what we're going to have to do is generalize that idea of breaking up our interval into subintervals and then using rectangles to approximate the areas under the curves, right? So there's a lot of notation here. It's a little bit notation heavy, but it kind of has to be in order to provide a general description of this thing as opposed to just being a single example. So, definition, let A to B be a closed interval if we choose n plus 1 points, x0, x1, x2 through xn in the interval, such that A, my starting point, is x0, x sub 0, and each subsequent x is larger than the one before it. X1 is greater than x0, x2 is greater than x1, so forth and so on, and xn is B, then the collection of subintervals x0, x1, x1, x2, so forth and so on, xn minus 1, xn, is called a partition of A to B. So in other words, what we're saying here is we've taken the interval from A to B and we've broken it up into a bunch of intervals from x0 to x1 and x1 to x2 and x2 to x3 and x3 to x4, so forth and so on. Now recall, last video, we were looking at just dividing up the intervals into even pieces, pieces that were all the same size. And now to generalize this, what we're saying is we can break up that interval actually however we want. We don't have to make all of the pieces the same size. It's convenient, it does make things easier, but we can break up those intervals into subintervals any way we want to. And definition, a sample point, x sub I star, is a point chosen from a subinterval, xi1 minus 1 to xi. So in other words, between x0 and x1, I pick a point. I call it x1 star. Between x1 and x2, I pick a point. I call it x2 star. Between x2 and x3, pick a point. Call it x3 star, so forth and so on. These are the endpoints or midpoints that I was plugging into our function to get our approximations in the last video. But here what I'm saying is, again, to generalize this, I don't have to pick endpoints or midpoints. I can pick any point inside the interval and use that point to determine the height of my triangle. Okay, and so now the big definition, a Riemann sum associated with a partition P, in other words, a way of dividing up the interval, a partitioned P, and a function f has the form, the sum from I equals 1 to n of f of x sub I star times delta x sub I. And again, that's just the sum of the heights times the widths of the rectangles. In other words, the sum of the areas of each rectangle. So you might call this like area 1, area 2, area n, so forth and so on. And here, delta x sub I is just the difference between xi and xi minus 1, because we can't have one general formula if we're making all the widths different. So graphically, what does this look like? It looks like this. It's the same basic idea we were talking about before, but now our rectangles are like all over the place, right? They have different widths. The sample points, like here, x sub I star, x1 star is here, so I put my height of my rectangle up here, right? Here, x sub 2 star is in this middle point, so that one we put there. Here, this x3 star is like a little bit off to the side, so we put the height of the rectangle at this point on the function, so forth and so on. But it's the same idea. You take the sum of the bunch of areas of rectangles, and it doesn't really matter how you divide up your partition. That Riemann sum is still going to give you an approximation for the area of the curve, or under the curve, I should say. Okay, so what did we say before? We said, hey, you know, if we could just take more and more rectangles, then the approximation would approach the real value of the area. And that's how we actually define the integral. So the real definition for the integral is if a function f is defined on the interval from a to b, the definite integral of f from a to b is the number, the integral from a to b of fx dx, that is the limit as the maximum of delta x sub I goes to 0 of the sum from I equals 1 to n of f of x sub I star times delta x sub I. That sounds like a lot, but keep in mind, what does this thing here? The limit as the maximum delta x sub I goes to 0. What does that mean? It just means the widths of the rectangles get small. So the reason we describe it this way, instead of saying the number of rectangles is going to infinity, is because we're allowing our breakdown of rectangles to be in any form that we want. And so we want to be able to guarantee that the rectangles get smaller. And so if the maximum delta x sub I goes to 0, that forces you to use more rectangles for the approximation, but it also ensures that each rectangle gets smaller. So what do I mean? So I mean, if I had a function like this, and the way I partitioned it was such that I used a bunch of rectangles over here. So on this right side, I just got like a ton of rectangles, all right? Boom, I'm sketching very quickly. It's a very ugly sketch. But I use a bunch of rectangles, but I only ever use one rectangle on this left portion. Well, it doesn't, if I divide up my rectangles that way, it doesn't matter how many rectangles I use, my approximation is always going to be off by this portion here, right? So by defining this limit in this way, this just says, not only do we need more rectangles, but also you have to make the width smaller so that you don't end up with this weird situation that I just drew up here. So other than that, it's saying the limit of the sums of the areas of the rectangles. Again, that's the areas of the rectangles. And we're just adding them all up. So in other words, the integral is the limit of the Riemann sums. That's really it. In shorthand, the integral is the limit of the Riemann sums. And that limit is the limit as the widths go to 0 of our rectangles. Now, of course, that's provided that this limit exists. And if this limit exists, we say that f is integrable on the interval from a to b. So we're not going to get into some of the weirder cases where an integral doesn't exist for a function. Some of that is really outside the realm of this class. But we do have a nice theorem that tells us when this limit exists. And this is really important because we know from limits early on when we were just dealing with two-sided limits, limits from the left and right, we knew that for the limit to exist, both the left and right-hand limit had to be equal. Well, here, this is much more complicated because there are infinitely many ways you can subdivide these intervals. And so, really, saying that this limit exists means that no matter how I subdivide these intervals, that limit gets the same answer. That's pretty tricky. So this theorem is very important because it tells us, hey, under certain conditions, you always get the same value for this limit no matter how you broke up your rectangles. So this theorem says if f is continuous on the interval from a to b, or if f has only a finite number of jump discontinuities, then f is integrable on ab. That is, the definite integral from a to b of f of x dx exists. And this is really important because if the that wasn't what I wanted to do. Let's try that again. I wanted to highlight that. This is really important because what this says is if the function is integrable, then I can pick any way of subdividing my rectangles that I want. And that leads us to the following three theorems. If f is integrable on a to b, we can apply the right hand, left hand, or midpoint integral theorems to evaluate the integral. And these are essentially just the natural extensions of those approximation methods that we looked at in the last video. So if we look here, the right-hand integral theorem says if f is integrable, then all I need to do is take the limit of the right-hand sums, which is the same thing as what we did before, just a limit, right? We pick our right-hand endpoints with x sub I equals a plus I delta x, and take the limit of that sum. That's our right-hand integral. Our left-hand integral is the same thing, except you've got I minus 1 instead of I in our formula for our sample points. And the midpoint integral, you use the average of the two. Now, the problem here with the midpoint integral is that this average is actually a little tricky. If you're doing a finite sum, you can just compute it explicitly for each average. Here, you really need to find the actual formula for the endpoints, which is fine. You can use your right hand and left hand formula for x sub I, right? The right hand endpoint and the left hand endpoint, and plug them into here and take the average. So I'm going to go ahead and do that real quick just to show you how you could get, should you need it, get that formula. X sub I bar is 1/2. I take the formula for the left hand. That's a plus I minus 1 delta x. Plus the formula for the right hand. That's a plus I delta x. And here we've got a plus a, that's 2a. And we've got I minus 1 delta x plus I delta x. That's 2I minus 1 delta x. And if I distribute the 1/2, that's a plus 2I minus 1 over 2 delta x. So you could always use that to compute your midpoints for your midpoint integral formulas, should you need it. Okay, so now let's try to apply this idea. First, we're going to express this limit of a Riemann sum as an integral, and we're given the boundaries from pi to 2 pi. So, okay, well, what's my function here? This is f of x sub I. So f of x is just sine of x over x squared. Remember, delta x is the width of the rectangles, and the translation to that, I should have probably mentioned this more clearly, is that when we go from the sum notation to the integral notation, where it is, delta x is the width of the rectangles in sum notation, and dx represents the width of those rectangles in integral notation. Now, it's a little bit tricky because it's the width of the rectangles after computing the limit as the width goes to 0, which is a complex idea for sure, but it's important that we maintain that relationship of the width and height in our integral. And as we get through more advanced integration techniques, you'll see how important that notation is then. But for now, we just think of translating this to our dx in our integral form. So our integral is from pi to 2 pi, that's the stated interval. The function is sine of x over x squared. and we change delta x to dx, and there's our integral. Done. Okay, now we're going to actually compute something. So find the area under the curve of f of x equals x squared for x between 0 and 1. So we're looking at the integral from 0 to 1 of x squared dx, and I'm going to use the right-hand theorem. So that means I'm going to take the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I delta x. And of course, x sub I is 0. It's a plus I delta x, right? So 0 plus I times delta x. What's delta x? Well, delta x is 1 minus 0 over n, or 1 over n, right? That's b minus a over n. So same thing we've been doing. Nothing different. The difference here is that we're not using a fixed n. We're asking what happens when n goes to infinity. Now that does make the computation more difficult, but not undoable. Okay. And let's see, x sub I here is I times delta x, which is I times 1 over n, or I over n. Okay. So now we can plug this stuff in. F of x sub I. Well, that's x sub I squared times delta x, which is 1 over n. And x sub I is I over n. So we've got to square that times 1 over n. I over n squared is I squared over n squared. But if I've got n squared down here times 1 over n, that's n cubed. And now here's the tricky part. Our variable for this is I equals 1. So since our variable is I equals 1, or sorry, it's not I equals 1, it's I. I don't know why I said I equals 1. Our variable is I. That means that anything in terms of n is considered a constant when it comes to the sum. So I is what changes in the sum, n is what changes in the limit. But that means that I can factor out my 1 over n cubed out of my sum. And so I just get left with the sum from I equals 1 to n of I squared. So notice this looks just like the problem we did before, where we had a specific n value, n equals 20, except we don't have a specific n value now. We're just working through this in general terms. Okay, so now this becomes the limit as n goes to infinity of 1 over n cubed times, and the sum from I equals 1 to n of I squared, we saw this before, is n times n plus 1 times 2n plus 1 over 6. Okay, so now we got to do a bunch of multiplication here. N times n plus 1, n squared plus n. And then in the bottom we get 6n cubed. Okay, and here we get n squared times 2n. That's going to be 2n cubed plus 2n squared plus n squared plus n, all over 6n cubed. And I'll rewrite that one more time. 2n cubed plus 3n squared plus n over 6n cubed. And now I take the same approach to evaluating this type of limit that we did at the beginning of the class. I multiply by 1 over n cubed, top and bottom. And then these terms go to 0. So I get left with 2 over 6, which is 1/3. Hey, that's exactly what we thought it would be. We were right. We were right. Great job. Okay, that's probably not all that shocking, but nonetheless, we did it. We actually computed it. It's tough. These are big computations to do. This is a complex problem to solve. Like, you got to keep in mind what we're really doing here. We're finding the area under the curve of this very awkwardly shaped thing that we cannot use any basic geometry formulas for, right? And we're trying to figure out this area by taking essentially infinitely many rectangles to approximate it, and then, taking a bunch to approximate it and going to infinity of those rectangles to actually evaluate it. But this is it. This is what we're doing. And that allows us to find the exact area under that very strangely shaped curve. Okay, so with that, let's go ahead and take a look at some integral properties. So a lot of these properties come straight out of the properties of both sums and limits. So if you think about what this integral means, and while I'm at it, let's talk about what this notation means. This symbol, it's a long S for long sum. Right? That's what the integral is doing. This whole thing is about these limits of these Riemann sums, right? That's what the integral is. So when I try to think of what the properties of integrals are, it all comes down to what the properties of sums and limits are. So if we look at the integral from a to b of c times dx, that's the limit as n goes to infinity of the sum from 1 to n of c times dx. But c is a constant, so I can pull it out of the sum and out of the limit. And then this becomes the limit as n goes to infinity of just delta x inside. So it's c times that limit. But delta x is b minus a over n. And so when I take the sum, I'm adding this same number. This is a constant in terms of the sum. I'm adding this number to itself n times, so I get b minus a times n over n. The n's cancel. That's the limit of b minus a, but again, that's now a constant for this limit. And so the limit of a constant is the constant. I just get c times b minus a. Of course, this is really easy to see in a picture, because if you look at the function y equals the constant c, you just get a horizontal line from a to b, and so the integral is the area, which is b minus a times c. The same thing. Okay, now property 2 here is that you can split up integrals on sums. Have to be really careful. A lot of students will make the mistake of trying to split up an integral on a product. You can never do that. But on a sum, you can absolutely do that. So let's take actually, I don't really need to talk. It's a long sum. I didn't write out an explicit proof of it, but it's kind of obvious, because what does this symbol mean? It means long sum, and we can split up sums on sums, so you can split up integrals on sums. Same thing. Property 3, you can pull a constant in front of the integral. Again, this is the same thing as factoring out the constant from a sum. So no difference there. You can split up the integral on a difference. Of course, that's the same thing as saying you can split up the integral on a sum, because subtracting just means adding a negative number. Now, these last two are a little different. So the fifth one here says the integral from a to c of f of x dx plus the integral from c to b of f of x dx is the integral from a to b of f of x dx. So here, we've drawn a little picture. So c is just some point in between. And what we're saying is if you take the integral from a to c, that's a to c of f of x dx, and you add the integral from c to b, what you get is the area all the way from a to b, which is what we've written here, the integral from a to b of f of x dx. And the last one, the integral from a to b of f of x dx, is the negative of the integral from b to a of f of x dx. In other words, if I switch my bounds, I make the integral negative. Or if I want to switch my bounds, I can make the integral negative. So let's look at a proof for this one. We've got the integral from a to b of f of x dx is the limit as n goes to infinity of the sum of f of x sub I times b minus a over n. That's my delta x. If I factor a negative out of the b minus a, then inside the sum it becomes negative a minus b, and I can move that negative all the way out in front of the limit. Now I have the limit, the negative of the limit of this Riemann sum, but my order has changed for b and a, so my bounds have changed for my integral. So now it's the negative of the integral from b to a of f of x dx. Okay, so let's use some of those properties. Here we've got a sum between my two terms. And so the first thing I'm going to do is split up this sum. I got the integral from 0 to 1 of 5 dx plus the integral from 0 to 1 of 6x squared dx. And what else can I do? Well, I have a constant multiple here, 6. I can pull that in front. And this first integral is 5 times 1 minus 0. This was property 1. Now the integral from x of x squared dx from 0 to 1, we already found that to be 1/3. So that was from a previous example. This was 5 times 1 plus 6 times 1/3, which is 2. So the whole thing is 7. So essentially, we just use these properties to rewrite the integrals until we can turn them into things that we already know the values for. And this is really important because, as you saw, it's really hard to evaluate these integrals. The computation is pretty heavy, and I certainly wouldn't want to have to recompute every one of these from scratch if I can use other theorems and other facts to make my evaluation much easier, much easier. Okay, so next, use properties and areas to evaluate the integral from -4 to 4 of 5x plus the square root of 16 minus x squared dx. So the first thing I'm going to do is split up my integral on that sum, the integral of 5x dx, plus the integral from -4 to 4 of the square root of 16 minus x squared dx. If we look at y equals 5x, and yes, we have seen these ones before, but now we're combining two of them together. Okay, from -4 to 4, the y value will be 20 up here, -20 here, and we get this area 1 and this area 2, and we know they're symmetric already, right? Because it's a line that passes through 0, 0, etc. We know that A1 and A2 are both equal, and they're both equal to 1/2 the base times the height. What does that mean? That means that area 1 minus area 2 is 0. So this first integral is 0. And now the second one, y equals the square root of 16 minus x squared. Well, we already talked about that one before. This is the semicircle at 0, 0 with radius 4. So it looks like this. And so the area here is 1/2 of the area of a circle, pi r squared over 2. So pi times 16 over 2, which is altogether 8 pi. All right. So now we've got if the integral from 1 to 4 of f of x dx is 11, and the integral from 4 to 3 of f of x dx is 7, find the integral from 1 to 3 of f of x dx. Well, I look at this and I think about this interval. 1 to 3 is what I want. I have the interval from 3 to 4 and the interval from 1 to 4. So I know if I take an integral from 1 to 3 plus the integral from 3 to 4, that should be the integral of the whole thing. So the integral from 1 to 3 of f of x dx plus the integral from 3 to 4 of f of x dx equals the integral from 1 to 4 of f of x dx. And so now I'll just replace the values that I know already. I know that the integral from 3 to 4 is 7, and the integral from 1 to 4 is 11. And so I'll subtract 11 minus 7, and I get the integral from 1 to 3 of f of x dx is 4. All right, let's move on to another similar kind of problem. But this one, there's something a little tricky about. So here, this integral is from 7 to 5. We've got the integral from 0 to 7, from 7 to 5, and 0 to 5. So again, it's another situation where I go, well, I know what 0 to 5 and 5 to 7. I know that 0 to 5 plus 5 to 7 would be equal to the integral from 0 to 7. But that's kind of a problem because that's not what I have. So this is the integral from 0 to 5 of g of x dx plus the integral from 5 to 7 of g of x dx should be equal to the integral from 0 to 7 of g of x dx, which would be great, except that these bounds are wrong. Well, how do I fix that? Well, I can just flip that integral over and say the integral from 0 to 5 g of dx minus the integral from 7 to 5 g of x dx is the integral from 0 to 7 of g of x dx. And now I can start plugging stuff in. So I get the integral from 0 to 5 of g of x dx minus 5 equals 8. And add the 5 across, and I get the integral from 0 to 5 of g of x dx is 13. Okay, so sort of one more big topic here, and then we're going to do just an extra problem or two. But here we have the integral comparison properties. So these are pretty straightforward for the most part. if f of x is strictly positive or 0 on an interval, then the integral is positive. That should make sense. All of the function's area is above the x-axis, so the whole thing should be positive. If f of x is greater than or equal to g of x on an interval, then its integral should be greater than the integral of g's. Again, this should make sense. F is bigger than g, so the amount of area under the curve should be bigger. We're assuming that, again, these are both positive here. Well, they don't necessarily have to be positive, but the picture assumes that they're positive for clarity. And 9, if f of x is bounded by some little m and big M, meaning I know that f is no bigger than this and no smaller than this on the interval, then the integral is bounded by little m times b minus a and big M times b minus a. And this picture should hopefully make that clear. This lower bound is the area of the rectangle that's at the bottom of the curve, the lowest point of the curve. And the upper bound is the area of the rectangle at the peak of the curve. That's it. So we're going to use property 9 to estimate the integral for sine squared of x dx. And so what do we know? We know that sine squared of x is between 0 and 1. It's squared, so it can't be negative, and sine is already between negative 1 and 1. So sine squared has got to be between 0 and 1. And so that implies that this integral is between the upper bound times b minus a and the lower bound, which is just 0, also times b minus a, but that's kind of redundant. And 2 pi thirds over minus pi thirds is 1 pi third. So in other words, we know that the integral from pi thirds to 2 pi thirds of sine squared of x dx has to be between pi thirds and 0. Okay. Now we're going to tackle this big one here. Use the right-hand theorem to evaluate the integral from 0 to 2 of 2x minus x cubed dx. So again, this is another one where we're just going to have to use that theorem. We're going to need to know, okay, what's delta x? It's b minus a over n, so that's 2 minus 0 over n, which is 2 over n. We got to figure out what our sample points look like, and we're using the right-hand theorem. So x sub I is a plus I delta x. So that's 0 plus I times 2 over n, which is just 2I over n. And now this integral we need to write as the limit of the Riemann sums. Okay, so I wrote my function in terms of x sub I, but now I need to actually plug x sub I in. So I'm just substituting 2I over n in place of x sub I. Okay, now we have to think about, okay, what's the goal here? So real quick, I'm just going to pull up the notes from our last video just to put something on screen here momentarily. Give me 1 second. And these are our summation identities from the last video. So the big goal here is that whenever we're doing these Riemann integral problems, we need to somehow write our sum as just the sum of I squared, or the sum of I cubed. So the goal is always to use our summation properties to rewrite the sums we're working with to where we can use one of these three formulas to evaluate them, or the constant multiple formula, that one too. Okay, so back to it. Okay, so how do I do that? Well, I've got my I, and here I'm going to have an I cubed. So I'm going to have to do a little bit of algebra first before I can do anything. So we'll just keep rewriting this algebraically. Two times 2i over n is 4i over n, in parentheses, minus 8i cubed over n cubed, right? I just took the 2i over n and cubed it, times 2 over n. And now I'm going to distribute this 2 over n. Gives me 8i over n squared minus 16i cubed over n to the fourth. And now I'm a lot closer to my goal of isolating my I and I cubed. What I see though is that I've got this difference between them. So the first thing that I can do is split up that sum on the difference. And so I get the sum from I equals 1 to n of 8i over n squared minus the sum from I equals 1 to n of 16i cubed over n to the fourth. And now remember, everything inside the sum that isn't a function of I is treated as a constant by the sum. So we can pull those things right out in front of the sums. And that gives us 8 over n squared times the sum from I equals 1 to n of I minus 16 over n to the fourth times the sum from I equals 1 to n of I cubed. And so we did it. Not the whole thing, of course, but we reached our interim goal of writing this in such a way that we get to apply one of those nice formulas. Okay, so now we're going to apply those formulas and see what we get. This is 8 over n squared times n plus 1 over 2 minus, so that was just my first sum formula there, minus 16 over n to the fourth times, and for the I cubed sum, that formula was n times n plus 1 over 2 all squared. So I'm going to write out like one more step of this, and then I'm going to kind of skip a little step on computing the limit because I want to save a little bit of time, but also it's all steps that I think you all will be perfectly able to handle on your own. First thing I'm going to do is this 8 over 2. That's going to simplify to 4 up top. So this is 4 times n squared plus n. I distributed that n all over n squared. Minus. This is 2 squared, and 16 up top. So that's 16 over 4. So that's going to be 4 times n times n plus 1 squared over n to the 4th. And there's a little bit of algebra to do here. So here we would multiply by 1 over n squared, top and bottom, blah, blah, blah. We've done a million of these. And we would see that this limit goes to 1. And here, we're going to see the same thing. You get n squared plus n, and then you square it, and your leading term is n to the 4th, plus some other stuff. And so this whole thing, this limit is also going to go to 1. And so the result of our total limit is 4 times 1 minus 4 times 1, which happens to be 0. It feels like a little bit of a letdown, of course, when you get through all of that and you're like, oh, it's just 0, what? But that's perfectly normal, perfectly normal. Okay, so that's it for this one. And let's see, let's double check. Yes, one last thing to talk about. So I've mentioned this earlier, but I just want to reinforce it as we wrap up this section. The most important thing to understand is that integration means accumulation. So we've taken a very deep dive into how to look at areas under curves, how to take these limits of Riemann sums and apply all of these properties, and it's a lot of material. But the main thing is to understand, why do we care about integration? And it's because integration means accumulation. So meaning if the function represents the rate at which something is being acquired, the integral is telling you how much of that thing gets collected. So, an example, if r of t was the rate that water poured into a lake, then the integral from 3 to 10 of r of t dt means the amount of water accumulated from time t equals 3 minutes until the time t equals 10. Just like when we look at the picture, it looks like the area under the curve is being accumulated as you move from left to right. That's what it represents, is accumulation of these real world things. So that's why we care about integrals and what we're going to be using them for. Now that is all we have for this one. So thank you very much for watching. Have a great day.